Today we are integrating the reciprocal function. Now, what is a reciprocal function? Well, a reciprocal is like a fraction that you can turn upside down, so that's how I remember that 1 over x is considered the basic reciprocal function. Now, we have already learnt how to differentiate logs, and we know that if we differentiate this, we get 1 over x. So then it makes complete sense that if we integrate 1 over x, we're going to get the natural log of x plus some constant. So we've got this rule here, but we're going to add to it in a moment. This is the base thing, it's not quite finished. Now I need to do some thinking. Remember that the basic log curve, which looks something like this, it's got an asymptote on the y-axis and it goes up this way, it has only positive values of x, doesn't it? So can you then graph the natural log of minus x? Yes, you can. And the right way to think this through is that if we compare this function with this one, x has been replaced with negative x. And if you're switching the x values from left to right or vice versa, you're actually making what we call a horizontal reflection, aren't you? And if you're horizontally reflecting this, it means that this graph is going to look like this, the complete opposite. We've just flopped it across the y-axis. So we can graph this one, okay, but we have to acknowledge that this one only exists for negative values of x, and this one only exists for positive values of x. So if we were to differentiate this function, and that makes sense, we might want to find the gradient of a tangent at any point on that curve, that seems fair. If we differentiate it, then our rules so far that we have learned tell us that this is a little function of x. So we put f dash x on the top, and differentiating this I just get minus 1. And we put the function itself on the bottom, minus x. What's minus 1 over minus x? Well, the negatives cancel, don't they? So we get 1 over x. We get the exact same result as we get for this graph. And that's sort of not surprising because we can see that they're just a mirror image of each other. They're obviously related. Now here's the tricky part. If we know that we can integrate 1 over x and get the natural log of x, isn't it also true from this result that we could integrate 1 over x and get the natural log of minus x if x is negative? Because if x is negative, what happens if you sub a negative number in here for x? A negative number like, say, minus 2, you'll get negative minus 2, and that's just 2, isn't it? Now, what we're saying here is that both of these functions differentiate to give the exact same thing. So when we're integrating them, we need to acknowledge that they can go two ways. What to do? Well, they're very similar. One's x and one's negative x. So what we do to get around it is we put absolute value brackets on our x here, acknowledging that if it's positive or negative, doesn't matter, we just take the positive version of it, and that gets us around this problem. So that's what I've written here. To make things simpler, we use absolute values in the formula. And this gives us a formula that works every time, okay? So understanding why we need those there really just relates to these two graphs, and that x could be positive or negative. We don't mind, we still get the same result. All right, now, something else to consider, and this is just a side note, I probably should have started with this, but before we knew how to differentiate logs, don't forget that we couldn't have differentiated this. Sorry, we couldn't have integrated this, because the usual rules create nonsense. Now, what do I mean by this? Well, let me show you a spare bit of board. If we integrated this, and we went, oh, we can't integrate because there's a fraction there, I know, we'll just rewrite it like this. Our usual rules, remember, told us to add 1 to the power. Well, what do you get when you add 1 to minus 1? You get 0. And then divide by the new power. X to the power of 0, well, that's 1, but we've got ourselves 1 over 0. So it doesn't really make sense, and that's this nonsense part. It's undefined for a start because it's got 0 on the bottom, and it's got a 1 on the top. We've lost our x's completely. So don't do this, and I'm showing you what not to do so that in case you go down this path at some point, you'll go, oh, that's right, I can't do it this way. I need to use logs. So if I'm integrating something that looks like a fraction, and here it might have been handy to write in your heading, integrating fractions, because it's tempting to look at fractions and think, oh, maybe I can undo the quotient rule or something like that, because when we differentiate, we get fractions in our quotient rule. But no, we're integrating something that looks fractiony, and what we get is logs. So it should be no real surprise following on then from our really simple rule. The slightly more complicated version is that if we differentiate a log of some function of x, we get f dash x over f of x. We've already learned this. So it makes complete sense that if we integrate something that looks like f dash x over f of x, then we're going to get the log of that function plus a constant. And you'll notice here again, the absolute value brackets that we had up here are again required. Why is that? Well, for a really similar reason. Just as x could be negative, and we need to look at the positive version of it, f of x could itself be negative, and we get the same sorts of issues. So we fix those by using absolute value brackets. And a few other things that we need to be careful of. We know that y equals 1 over x is a hyperbola, and it's got two branches. Remember that it looks something like this, with asymptotes here and here. So it's effectively two separate graphs when it comes to integrating. And this means that you can have different constants of integration in each branch. So treat each branch separately when you're finding your integrals and your areas. Now, all I mean by different constants of integration is that if we're integrating to find an area, that's one thing, but there's another time that we integrate. We integrate sometimes when we know what f dash of x is, and we're trying to find f of x. And when we do that, we need a clue, because integrating it gives us a basic idea with a plus c on the end. If we then have a clue of some point on the curve, we can use that to work out exactly what the function is. But bear in mind that you might have a different plus c on this section and this section. Now, the other thing we need to take note of is that you can't integrate, or differentiate for that matter, across an asymptote. So always check your bounds on any questions with definite integrals or areas to check that you're not crossing one. Now, this first example actually gives us a really nice simple result. With any question, always bear in mind what it is that you're finding, so it stops you making mistakes. We're looking at the graph y equals 1 over x, which we know is a hyperbola like this. We're not really interested in this bottom branch because we're looking at the bounds x equals 1 and x equals e, which looks something like this. And we're finding this definite integral, which is also the area under the curve in that point. Now, we know we've got positive values of x, so that whole absolute value idea, we don't really need it, but let's just use it as good practice so that when we do have one that's negative, we won't be caught out. So we need our square brackets, we need to integrate 1 over x, and we get this result straight out of our formula, and our bounds, e and 1. On the next line, we sub in e, and then subtract the subbing in of 1. So we've got the log, natural log of absolute value of e. Now here, I don't really need to put those brackets on. As long as you're considering that the number you're putting in is positive, you can jump straight to this. It saves you a line of having to get rid of those absolute value brackets. And then we're subtracting the log of 1. Again, no real need to say the absolute value of 1 because I know in my head that is 1. Now I can see that e to the power of 1 is e, so this whole part here is 1. And this whole part is e to the power of something is 1, and that's 0 actually. So I've got 1 minus 0, so I'll just stop there and say that's 1. Now this result is actually quite interesting. There's lots of different definitions of that special number e, and this is another one of them that we haven't really seen yet. E is the special number at which, when you look at the area underneath this curve, it gives you an exact area of 1 unit squared. Example 2 doesn't have any bounds. That means we don't need the square brackets. We need to integrate this thing, and then we just need to remember to add a constant at the end. Now, you'll have some questions that I would call a perfect question. It's just ready to go, and others that aren't perfect, and you can rewrite it how you want it, then adjust for it. This one's nice and simple. It's what I'd call a perfect question. And the reason it is because I'm looking for f dash x over f of x in the thing that I'm trying to integrate. Because if I've got that, I know that I've just got the log of whatever is on the bottom of that fraction plus c. Now here, if I differentiate x squared plus 2, I just get 2x, and that's exactly what I've got on the top. So it's ready to go, and I can reason that I've got the log. Oh, I should remember there's absolute value brackets here. Now, the reason I didn't think of writing them down is because I'm just looking at this example, and I know that x squared plus 2 is always positive. How do I know? Well, x squared is positive, and if you add 2, it's still positive. So you can put absolute value brackets in there if you like, but in this case, they're almost not necessary. You could even have round brackets, and then you need the plus c. Now, why have any brackets at all? Well, you need to be a little bit cautious, because if you write this, that can be really unclear whether or not the 2 is part of the log or whether it's just tacked onto the end. So brackets help show that we're taking the natural log of x squared plus 2 rather than the natural log of x squared and then adding 2 to it after, because they're two separate things. So if I'm going to put brackets anyway, then I suppose they might as well be absolute value brackets. They're not wrong to use them, but someone with round brackets on this question would get it completely right as well.